Now that we have a firm understanding of electron configuration, we can introduce the concept of valence electrons. Valence electrons are electrons that are in the highest energy shell, or principal energy level. These are the electrons that do the chemistry, so we care a lot about them. All the other electrons are in lower energy shells. They don't do chemistry, and they're known as core electrons. So many of the chemical and physical properties of atoms are determined by the number of valence electrons that they have. So let's look at the electron configuration of rubidium, which has 37 electrons. If we look at its electron configuration, we can clearly identify that 5 is the highest energy level. There's 1 electron in the 5th energy level, so rubidium has 1 valence electron. The rest are core. Krypton has 36 electrons. If we look at its electron configuration, we clearly see that the highest energy level is the 4th, and so therefore it has 2 plus 6, 8 valence electrons. Now if we draw out the condensed electron configuration, we'll still be able to see our valence electrons. Our valence electrons are never part of the noble gas configuration. Okay, so determine the number and types of valence electron in an arsenic atom. Not exactly sure what they mean by type, but just write out the electron configuration and see if you can figure out how many valence electrons arsenic has. So here's arsenic on the periodic table, and it has an atomic number 13, so therefore it has 33 electrons. So you can either use the periodic table or the little diagram to help you figure out its electron configuration. Whichever method you chose, this should be your final electron configuration. And you'll notice that the highest energy level in it is the 4th. There are 2 electrons in the 4s subshell and 3 electrons in the 4p. Therefore, there are a total of 5 valence electrons. And I guess what it meant by type is that they're in the S and the P subshell. Now in this class, we are mainly going to be concerned with the valence electrons of the main group elements. And by main group, we mean the S block and the P block. And it is extremely easy to determine the number of valence electrons just by looking at the periodic table. The valence electrons of this family is 1. The valence electrons of this family is 2. We skip the D block, and then 3, 4, 5, 6, 7, 8. All we have to do is count from left to right, ignoring the D block. And also, you need to remember that helium does not have 8 valence electrons, since it only has 2 electrons total. The 8 valence electrons are for neon and below. So this diagram here has the S block and the P block for the first 3 periods, and it has the valence electrons written out. The core electrons are not written. So here's hydrogen, 1 valence electron. Here's lithium, 1 valence electron. Here's sodium, 1 valence electron. Here's our second column, our alkaline earth, beryllium 2, magnesium 2, and if we continue down and looked at its electron configuration, every single member of the alkaline family, alkaline earth family would have 2 valence electrons. Here is our first member of our P block. Every member of the boron family is going to have 3 valence electrons. Every member of the carbon family is going to have 4 valence electrons. Every member of the 5th of the 5A group or nitrogen family is going to have 5 valence electrons. Every member of the oxygen family is going to have 6 valence electrons. All the halogens are going to have 7 valence electrons, and except for helium, which only has 2 electrons total, all of the noble gases are going to have 8 valence electrons. And if you draw out the electron configuration for all of these, you will see that is the case. But you don't need to do that. If you need to figure out the number of valence electrons, all you have to do is count from left to right, ignoring the D block. Elements in the same column have similar chemical and physical properties because their valence shell electron configuration is the same. The number of valence electrons for any main group family is going to be the same as the group number, which we saw up here. 1, 2, 3, 4, 5, 6, 7, 8. Now, just to recap, for the main group elements, the number of valence electrons is the same as the column number except for helium, which only has 2 electrons. Now, the transition elements are in the D block, and I have to respectfully disagree with the textbook that says the number of valence electrons is usually 2. We won't be looking at the number of valence electrons for the D or the F block too much because it's a little bit complicated. If you go on to Chem 151, we'll look at it in detail. So we really just care about the main group elements in terms of the valence electrons. So we're just going to ignore the D and the F for now. Although if your homework asks for the transition metal, it's wanting this too. But I do have to tell you that this is a pedagogical lie. It's not really the case, but for our purposes, we can just leave it at that. So get out your periodic table, pause the slide, and determine the number of valence electrons for sodium and tellurium atoms. Here's sodium right here in our first column, so it's going to have 1 valence electron. And tellurium is over here. 1, 2, 3, 4, 5, 6. Every member of this family is going to have 6 valence electrons. We count from left to right, ignoring the D block. Now, if we took a look at its electron configuration, we can see that 3 is the highest energy level for sodium. There's 1 valence electron there. And if we were to draw the orbital diagram for it, for the valence electron, this is what it would look like. 1 unpaired electron. And if we drew out the electron configuration for tellurium, we would see that we have 6 electrons in our 5th energy level. 2 plus 4 is 6, 6 valence electrons, and after our noble gas configuration, this is what our orbital diagram would look like. But only our 5s and our 5p are going to be considered our valence electrons. Even though the D is close in energy, it's just always the highest energy level. And taking a look at that orbital diagram, we see that we see that tellurium has 2 unpaired electrons when we draw out its orbital diagram. Because remember, we want to keep our electrons unpaired as long as possible.